yesterday you factored polynomials and set them equal to 0 to find their roots, or values that when you substitute them back into the polynomial will give you 0. Today you're going to work with polynomials that cannot be factored, but there's another technique that you can use. So today I want you to be able to use the rational root theorem and the irrational root theorem to solve polynomial equations. So not all polynomials are factorable. However, the rational root theorem can help you find all possible. Now I've circled that possible because it gives you actually more possibilities than what you need, but it narrows it down from infinity. So it is helpful. So all possible rational roots of a polynomial equation. And notice it says all possible rational roots. So when you use the rational root theorem, some of the possible roots may not actually be roots. The rational root theorem narrows down the possible roots from an infinite number of possibilities to a more manageable amount. So if you don't use this theorem, then you would just be blindly plugging numbers into the polynomials until you find something that works, and that could take forever with certain polynomials. So this will narrow down all the possible ones, and then you'll have to test the possible ones. So you'll be using the rational root theorem and also the irrational root theorem. So irrational, we're going to have square roots that can't be simplified. Okay, what we're going to do is if a polynomial has p of x has an integer coefficient, then every rational root of the polynomial can be written in the form p over q, and I'll explain that in just a minute. But here it's explained as where p is a factor of the constant term and q is a factor of the leading coefficient. Now the same is true with the irrational root theorem, but with the irrational root theorem you're going to have, like I said, square roots or square roots of something that the square root's not going to go away, and irrational roots are going to come in pairs. So, for example, if 3 minus the square root of 2 is a root of a polynomial equation, then 3 plus the square root of 2. So its conjugate is, when I say they come in pairs, I'm talking about its conjugate. Okay, so to identify p and q, put your polynomial in standard form. P will be a factor of the constant, so the one without the variable, and q will be a factor of the lead coefficient. So watch your p's and q's. The reason why I say that is because when you have a polynomial, and you don't need to write this down, but if you have 4x cubed plus 2x squared plus 6, and I say find p and q, and you know when it's in standard form, they're going, after you pull out the GCF if you need to, then you're going to have the first number and the last number, but p is at the end. Q, because it's the constant, Q is the lead coefficient. So don't switch those two around or you're going to run into some trouble. So just remember, if your mother has ever said watch your P's and Q's, she's mind your manners, but that's what you need to do when you're identifying P and Q for a polynomial. So when finding the roots of a polynomial equation, always try to factor first. Now, you don't have to. You can use P's and Q's first, but usually it's more work to do that. If the polynomial does not factor, we have an extra letter here, just cross that off. Use the rational root theorem, which would mean P's and Q's, or the irrational root theorem, depending on what your polynomial is. Okay, so here are the steps that you need to follow. The first thing is you need to put the polynomial in standard form and set it equal to 0. So this particular problem, we're adding 2 to both sides, and then we set that equal to 0. Then you're going to write all of the factors of p over q. So factors are numbers that would divide a number, and you would have no remainder. So all of the factors, we're going to identify p first here. This is p, and this is q. And all of the factors are p, so of p would be plus or minus 1, plus or minus 2. So positive and negative 1 can both divide 2, and positive and negative 2 can both divide 2. And then, so we have p and q are the same in this case. So we have positive and negative 1 for a denominator. Once you list all of the factors of p, put them all over the factors of q, you need to list every single combination that you can of P over Q. So we're going to, best thing to do is just to pick one number, the first one here, and put it over each one. So we would do 1 over plus or minus 1 over 1, plus or minus 1 over 2. And then go to the next number, plus or minus 2 over 1, plus or minus 2 over 2. So our possible roots are right here. Positive negative 1 over 1, positive negative 1 over 2, positive negative 2 over 1, positive negative 2 over 2. Now that equals 1, so sometimes you'll get duplicates. So basically when we put these together, we're going to end up, the possibilities for roots for this polynomial would be a positive 1, a negative 1, positive 1/2, negative 1/2, positive 2, negative 2, positive 1, negative 1. Now this polynomial only has 3 roots. So some of these are not going to be roots, but we know that we can find at least one in here. So what I'm going to do is test these roots. Now you may think, oh, I have to test all of those, but it's better than just shooting in the dark and, trying a ton of different numbers. This narrows it down to just 8. So the first thing that we'll do, we'll try a positive 1. So we use synthetic division, and we're going to test it. Now, this particular polynomial is missing an x to the first power. So we need to put in a 0 for placeholder. We're going to take the variables out, and we're testing 1, so that goes in the backwards L here. And then we put 2, the negative 9, 0 for the placeholder, and 2 for the constant. Okay, just a reminder, I've already written this out, but I'll just step you through this. Reminder for synthetic division, you drop the first number down here, which is 2. Once it's down here, you multiply. You put the product above the horizontal line, and then you add. Once it's below the horizontal line, you multiply. So negative 7 times 1. Above the horizontal line, you add. So that'll give you negative 7. Multiplying again, we get negative 7 here. Adding, we get negative 5. Okay, this has to be a 0 in order for 1 to be a factor. So this is not a factor. We need to test another number. So we tested 1, and I know which one will work. So we'll just, instead of keep testing more, we'll just go right to 1/2. That one is going to work. Probably shouldn't tell you that right now. But okay, so we'll put 1/2 here. We'll put our values in here again. And then we're going to do the same thing. We'll drop the 2 down here. 2 times 1/2 is 1. When I add that to negative 9, I get negative 8. Multiplying, I get negative 4. Add, I get negative 4. Multiply, I get negative 2. Add, I have 0. This must be 0, so this is now a factor. 1/2 is a factor. Okay, now, when you get down to a quadratic, which means a degree 2, I would try to factor or use the quadratic formula. And I'm going to use the quadratic formula on this one. So I really don't need to put the x's back in here. I know that this is A, this is B, and this is C. So you had a lot of practice with the quadratic formula, and remember that's x equals, well, I can write it over here if you need it, x equals negative b plus or minus the square root, b squared minus 4ac all over 2a. Okay, so here is negative b, because b was actually a negative to start with, so it ends up being a negative 8. So it's going to be 8 plus or minus the square root of negative 8 squared minus 4 times 2 times negative 4. All of that goes over 2 times 2. All right, now you just need to simplify this. And when you simplify, you'll end up with 8 plus or minus the square root of 64 plus 32. All of that is over 4. So I'm simplifying some more here. And I end up with, well, let's just go here. I ran out of space here. I guess I didn't leave enough of space. So we're simplifying here. We end up with 8 plus or minus the square root of 96 over 4. Now, there are some perfect squares in 96. So you can do a factor tree. And when you do a factor tree, you'll find out you have 1, 2, 3, 4, 5 2s and a 3. So we can pull these out, circle the pairs. They come out as just a 2 here. And then that leaves me with 8 plus or minus 4 times the square root of 6, and that's over 4. Now, this can be reduced. We have to be able to divide all 3 of these by the same number, and we can. We can divide them all by 4. So that is going to give us 2 plus or minus the square root of 6. Now, remember, The degree will tell you the number of roots. So we have a degree of 3 here, which means I should have 3 roots. Well, let's look here. I see 2 here. I know that I have 2 plus the square root, 2 plus the square root of 6. I also have 2 minus the square root of 6, so that's only 2. The third one was right here. We found the factor by doing synthetic division and ending up with a 0. So that whenever you get a 0 for a remainder, this is always, I think I said a factor, but that is actually a root. This is a root and these are roots. So we'll do 1/2 here. Okay, so now you have 1/2. So these are your 3 roots. Polynomial said you should have 3 roots, and we do. All right, there's one for you to try on the back of the sheet.